Hello ARRL members and readers. I'm Dave Kassler, amateur radio call sign KE0OG, the author of the Ask Dave column in QST. This is the supplemental video that expands upon the September 2022 column. The second question in the column was about audio hum from power supplies. Figure 2 in the column is notional. Let's take a look at Figure 2b. Here we show the unfiltered output of a full wave rectifier superimposed on the power supply's output. As I said, this is notional. This video looks at an actual case of a full wave rectifier followed by a capacitor for a filter. And then we will look at the output on an oscilloscope to see what the output waveform actually looks like. We're going to use a kit I just built, the Amico AC1T. It's a retro kit and has tubes, both for the rectifier and the oscillator. It's an actual duplicate of the original AC1T and has both the advantages and disadvantages of something from that era. I recently released a video on my YouTube channel about this kit. Let's take a look at the schematic. If we look down toward the bottom, inside the circle, we see a classic full wave rectifier. The filter portion of the power supply consists of a single capacitor. Now, to see the difference between a full wave rectifier and a half wave rectifier, we can look at this diagram from a 50-year-old ARRL amateur training manual called Understanding Amateur Radio, which at the time was the study guide for the general class license. This was long before the FCC released the questions in advance. Figure 12.1 in the 1971 edition shows two rectifiers. In A is a half-wave rectifier. The output is a series of bumps called pulsating DC, with the bumps occurring 60 times per second. In section B, we see a full-wave rectifier, just like is in the Amico. Again, the output is a series of bumps, but as you can see, they are far closer together and actually occur at 120 bumps per second. And now for the conceptual leap. We add a capacitor to the output as shown in the 2021 ARRL Amateur Radio Handbook, Figure 7.6. In section C, we see a half-wave rectifier and bumps that are coming at 60 times per second. Now note in section C that there is a capacitor in the output circuit. The resistor labeled R is actually representing the load. Note what happens. The output of the rectifier charges the capacitor. The capacitor discharges through the load. For a load that draws constant current, the capacitor drops in voltage linearly with time. Then, when the next bump comes around, it boosts the capacitor voltage back to the top, and then this repeats. As an aside, note that there is a bleeder resistor across the capacitor, so the capacitor will not retain its charge after the unit is powered off. This is for safety reasons. We can see this more clearly in this blown-up drawing. You see the bump, actually the top of the bump, and in magenta you see the capacitor discharging between bumps. Then when the next bump comes around, the blue line shows the capacitor recharging. So, and this is important, there is a constant charge-discharge cycle going on. The output to the load has what is called ripple. Now, in the Ask Dave column, I show the ripple as being the bumps themselves, but with an output filter, the waveform is somewhat more complex. So, I grabbed the Amico rig and connected an oscilloscope probe directly across the high voltage. Note that my oscilloscope will handle pretty high voltage, and the 350 volts in the Amico is no problem. Now, the transmitter has two states. The first is idle, in which the oscillator is switched off, which corresponds to the key up situation. The oscillator draws very little current in this state. So let's look at the oscilloscope photo showing the output voltage when the oscillator is switched off. It shows very little ripple. In fact, according to the oscilloscope, the ripple is only 1 volt peak to peak, and the output voltage of the power supply is 368 volts. That's very good. Now, the amount of ripple is too small for the oscilloscope to accurately measure the frequency of the ripple. So I did it by hand and found that the frequency is about 120 hertz, as you would imagine with a full wave rectifier. Now let's look at the case where the oscillator is loaded. This corresponds to key down, or transmitting. This is shown here. Again, you can see the same shape of the curve. The capacitor recharges at the top of the bump, and then it discharges quite linearly until the next bump comes along. Note that our maximum output has dropped to 305 volts, and the ripple is 7.2 volts peak to peak. Now, the waveform here does not look exactly like the handbook waveform I showed you earlier. The reason for this is because the waveform shown in the handbook has a very sharp corner. To create corners like this in real life, we need almost infinite bandwidth. We don't have that in real-world radio, so the charging curve is somewhat smoothed out. So, what have we shown? We have shown that for old-style rectifiers, such as are included in vacuum tube circuits, the voltage can vary quite a bit depending on the load. We also discovered that the greater the load, the more the ripple. Now, I want to point out something that some of you may be thinking. Okay, the plate voltage has this ripple on it. This ripple is at an audio frequency, 120 hertz plus harmonics. Note that a major method for AM modulation is to put an audio waveform on the plate supply voltage. That means that this ripple waveform will appear on the CW output of this little CW transceiver. In other words, it will be slightly modulated with this 120 hertz tone plus its harmonics. This will give the transmitter's tone a less than pure sound in the listener's receiver. In other words, somebody who is listening, who provides a true RST, will not give the tone a 9. Now let's translate this into modern supplies. A modern power supply has an active circuit that smooths out the ripple and can also keep the voltage constant. But that's a story for another video. In summary, the actual ripple that appears in a full wave power supply, especially a high voltage power supply, will create a ripple with the fundamental frequency of 120 hertz. However, note that the waveform, though periodic, is not a sine wave. In addition to the 120 hertz fundamental, there are harmonics that appear at multiples of 120 hertz. This is why in higher quality transmitters there is more filtering. We have seen how a power supply rectifier creates pulsating DC. We have seen how a simple filter, like a single capacitor, is recharged every time a bump's voltage exceeds the capacitor's voltage. This creates ripple. The ripple varies according to the load, and without additional filtering, will find its way to the output signal. Fortunately, modern power supplies, both linear and switching, operate on a somewhat different principle and have very little ripple. So there you have it. I'm Dave Kassler, amateur radio call sign KE0OG, with a supplemental video for the September 2022 Ask Dave column. If you would like to ask a question for me to answer in the Ask Dave column, please submit it to AskDave, all one word, at arrl.org. If I cannot answer it in the column, I may answer it in an Ask Dave video or directly via email. Keep those questions coming. Until we next meet, 73.